Hi, I'm Ed Sperling. I'm the editor-in-chief of Semiconductor Engineering. I'm here at Barrie Mullins at Flex Logix. Going to talk today about simplifying AI edge deployment. Barrie, when you think about AI, typically most people equate it to what's going on inside the cloud, or it's a very, very customized chip that has been developed for a very specific purpose on the edge. But the inferencing doesn't necessarily need all of that power and compute complexity. At the same time, you want to be able to develop one chip and have it run in multiple places. How do you do that? How do you make it work so that it can be done fairly simply? Average company can do it as opposed to you have to put teams of 20 developers on it.
What a lot of people need to be able to do at the edge is they have to compete for the compute, the performance, and power aspect that's there. It's very, very different to the cloud or central computing or large servers. And it's usually in a location, and the edge is where technology meets humanity, and these things begin to interact. So what people are doing in order to make these systems easy to design and apply AI on and then deploy is the traditional mechanism that an embedded system now has an acceleration chip that goes in there that is designed to be very flexible yet power efficient from a compute perspective. And it can now do AI models and run them efficiently at the edge, because you need the embedded compute power, you need other parts of the system that are out there. You now need to add a chip that can add the low power but high performance compute that AI needs. And as AI models develop over time, that chip needs to be able to cater for those different models. If you think of where we started with AlexNet and look at where we are now with YOLO v6 and YOLO v7 and such models coming out, and a lot of the natural language processing models that are now being transferred over to the vision side using transformers, it's very, very different technology and has different requirements from a compute perspective. And what we've done is we've developed an underlying hardware architecture that is completely reprogrammable and scales very efficiently to be able to run all of those different models in the hardware next to people to be able to process and see or interpret what's going on, allowing an application to then make decisions or to push information back to other locations or to other systems that can then act upon what the AI is interpreting.
Let's take a closer look.
Sure.
Barrie, what are we looking at?
So this is an AI workflow for development and deployment of AI at the edge. This is kind of my high-level view that I use to communicate internally and externally with people about what is happening with AI, how does it work? And it really moves from left to right in terms of AI data operations. And this is where people that want to deploy AI, they have data. That data needs to be put into a format by which it can be used to then train a model. And when you do the training of the model, you move into that middle phase, which is the model development operations phase, or what I call DevOps. And this is where that data and either past models or the data itself becomes a new model. And what you're doing is you're training the AI algorithm based on all of that imagery and data that you've captured so that it can detect or classify the information that you're looking for and give you an output. Once you've got a model in a specific format, you then need to optimize that model for deployment, which is the right-hand side here, which is the machine learning operations piece. And that optimization is really targeting that edge product or the edge accelerator so that you're able to run efficiently and accurately and also take advantage of the low power and the acceleration that you get from our Hawk and X1 chips at the edge.
One of the challenges that a lot of companies are wrestling with here is that In order to make this efficient, really optimize it for whatever you're trying to do, you've got to take the algorithm that you're working with and optimize it for the hardware, and then optimize the hardware for the algorithm. How does that work here?
The two aspects of optimizing the model for the hardware and optimizing the hardware for the model are quite complicated, and the interaction absolutely needs to happen, because as you develop and you take a model and deploy it at the edge, what you're going to find is new data at the edge that forces you to go back and change that model because of, maybe it's lighting, maybe it's seasonal, maybe it's the time of day, maybe somebody's bumped into a camera and they've moved it a couple of degrees and it's no longer focused on the same thing, and you need to update the models. And the optimization of a model relative to the edge is basically to take advantage of something that can run at a lower power and lower performance. But you need to maintain that high accuracy of the model, and you don't want to lose that as you go from the model development side into the machine learning operations side. So a lot of tools and time are spent in building that model so that you can maintain the accuracy, but yet cut it down to a smaller model and make it very, very efficient for the edge.
So what happens when you have a device that's out in the market for, say, 5-10 years, and the algorithm changes, it gets updated over time? How do you update the hardware with that?
There are a couple of different ways that companies are addressing how you update the hardware over the life cycle. Many are developing products that are updated, on a 2 to 3 year cycle from a chip perspective. And it's a plug-in card. It's very standard form factor. You can take today's card, unplug it, take a new card and just plug it in. Software is designed to be compatible across that. But for products that you can't actually do that update easily, it's really important that the underlying architecture is able to continue to grow and change and run new models, even if it doesn't run them at the same performance as maybe new technology. Because something that's deployed today that has to exist or persist for 5 to 10 years, you want it to be able to run the new models in a way that you at least get answers and updates, and not to have it just completely fail and not be able to run those new models. And we're fortunate with our architecture, because it's a reconfigurable hardware system that is programmed in software, we are able to scale to many of those models. And that's what we're seeing as people move to transformers, and as they move to new models with more parameters, and that traditional technology has not been able to scale the same way. And we're fortunate with our architecture and our inventions that we're able to do that.
So how do you actually address this workflow? What changes here?
So it's not so much that things change here. What we're doing here is we work with customers and they keep their data and they do their data operations. They actually develop the models through the standard flow that they would use in the industry today. We're not asking them to change any of the front end of that or the left-hand side. And halfway through the model development operations, pretty much everything stays the same. Once they have a model in that final format, they can then use our InfraX model developer kit to be able to optimize that and quantize it and compile it down to take advantage of our accelerators. And then our accelerators are deployed in hardware in a couple of different form factors. You can see one of them here. And then you use what we call our InfraX runtime kit to be able to configure and manage that edge device, to be able to call models, run models, load new models, receive new models and update them. And then we have, of course, some application software that people tap into. So it's really about enabling people, after they've developed their model, and that they can do that in the traditional way, to really make it efficient and effective to go through those last steps, and then to be able to manage it over that full life cycle.
One of the key variables when you think about inferencing on the edge is accuracy. That affects both performance, it affects how much power you're using. It also affects how much heat you have to dissipate as you go forward. How do you deal with that? What changes as you go into different markets?
Think about a lot of the AI chips and capabilities that we build out is that it's very transferable across many, many different applications. As I explained earlier, customers are able to take their data, they can build models doing transfer learning, They can do that in a couple of different ways. And then they get out a standard, what we call floating point 32-bit model, or FP32 model. And it's from there that we then look at how do we optimize and quantize that model to get it down into something that can be much more efficient and effective at the edge. So it reduces the amount of power that's used, reduces the thermal profile of that system, yet is still very efficient and delivers the accuracy. And we do that with our tools, our InfraX compiler, and we deliver the form factor, we call it a model, in an NCF model that goes out, and then that's what's run on our hardware. But at the same time, we also kick out an int8 model, right? That's an integer 8-bit model. That is the same model as the FP32, but it's got all those optimizations in it. Customers can then take that model and run all their data through it, the same as they would in their standard learning process, to see how that model compares against the floating point 32-bit model. And our goal with many of the models that we create for our Easy Vision product, or that we're working with customers, is to get them down to a 1 to 2% accuracy drop in total as you go from FP32 to int8. And you can reduce that accuracy drop by having better data, more data, and going through that whole learning process, and then doing the compilation and the optimization.
Just to be clear, that quantization is all about how much accuracy do you need, how do you achieve that accuracy, and how far can you push that accuracy without really affecting the performance and power, right?
Yes, so quantization is really about, one, getting the model down to be smaller so that it is much more efficient from a power and performance perspective, and a thermal perspective, but not losing the accuracy, right? You want to maintain that accuracy. If you have a system that is required to be 99% accurate, you don't want to have that dip to 96, 95, 94, because all of a sudden, whatever dependencies you have on that can be lost. So the quantization is really important in those steps, that you understand that even though you're dropping the data down from a larger size to a smaller size, that you maintain the integrity of the model at that high level. But the other part about the quantization is to make it very efficient so that you can run it on a device that doesn't necessarily have the same power or compute that you would have in a data center. It may be in a battery device, it may be in a device that's driven by some solar panels, or it may be in an autonomous machine like a robot, or in a factory floor that has power next to it, but is not what I would call a very conducive compute environment. So you're really trying to optimize and balance that power, performance, yet maintain the accuracy. And that's the key to quantization.
And this is one of the balances that you have to strike as you move forward too, right? Because what you're looking at is maturing the algorithm through better data, and you can understand how that data gets applied, how it gets used by the inferencing chip, and then also how the quantization can improve that over time. And then you also have to worry about, is this getting obsolete? Do we have to update it for other stuff, that with other features that potentially can creep in here?
Yeah, absolutely. Anybody who's developing AI and has developed or deployed a product with AI fully understands, or if they don't, they will quickly learn that once you've deployed the model, it's now engaging and interacting with people and the environment, you're going to get new data. You're going to see things you didn't see before, or you're going to see use cases that are new and developing and evolving. Those use cases and that data needs to go back into the system to go back to the start of the flow, to upgrade the models, to create new models. Those new models can be more complex, and that's where quantization for those newer models becomes critical, so that you can continue to run them at the edge, and you can extend that lifetime and the life cycle of your product by having the data updated on a regular basis and the models updated on a regular basis.
So how long does it actually take from start to finish, if you're developing a product with an inferencing chip, to have it fully functional and good enough for whatever you're trying to do?
It depends on the type of product you're trying to build. If you're building something with a chip down, it can take a lot longer. But what we're doing is we're enabling customers with standard form factors. And we have an example here where we have our Hawk board, which has everything on it that people need to be able to put it in a box, put their application software down on top of it, and then deploy it. And because of our tools and the software that we put in there, all you need to do is plug in a power supply, switch on the board, it will boot the operating system. If you have an application that you've written, you can then run that on this board. And the underlying software that we have built into this allows you to access, one or two of our X1 accelerators to be able to do AI. So there's an aspect of hardware and software readiness that's required. In other cases, people will need to design custom carrier boards or custom chassis, and that can extend the overall time. But the key is having a platform that's ready to go with operating systems like Windows and Linux that boot immediately, and all of the hardware underlying that abstracted so that people can take advantage of it from a software perspective, write their applications and deploy them very easily and in a standard traditional type of manner.
So where do you see this actually taking off? What types of markets would be using inferencing chip and trying to develop it so that it's quick, they can maneuver it to multiple different products and potentially even within the same product?
The customers that we're engaged with, and we see a lot of our on the safety side of things and security side of things, where people are connecting up cameras to be able to ensure that areas are safe or that people or employees in those areas are safe. And they will be able to take a box like this, take cameras that they've already deployed, maybe in a building or in a construction site, and just be able to take the camera, plug it into this system. Or most of the cameras today are either Ethernet or USB based, and they can just plug it into this system. The application software on top of this can then take advantage of that infrastructure and start doing detection and classification on the various different things that are happening. We also see a lot of adoption and interaction in the industrial optical inspection space, where people are seeing a huge number of products and manufacturing quality and a requirement for assistance to be able to detect and determine defects earlier in the system. And the earlier you can do that in the system is a way that you can reduce the impact of a defect or a quality item. And at the same time, you can improve yield and performance of that whole manufacturing process. So a lot of optical inspection systems, again, they're camera-based, can take advantage of this. Traditionally, a lot of that's been done from a computer vision perspective, but with AI, you get much, much better performance and accuracy results, which goes back to the piece we were talking about earlier. And also, it allows you to update and train the model over time so you can cater for many different products or different product variations. And it's much faster than if you had to code it in a traditional computer vision manner.
So how much expertise do you actually need in order to work with this? Is this the same as I'm going to develop a complex ASIC, or is it much simpler than that?
It is quite complex if you're developing a model from scratch and you've got to go and collect your data and set up your data. But we've created an easy vision product that actually delivers application ready models that people can just use. And as I said, you can switch on the board, boot it up, the operating system will work, and these models are readily available for people to use. So if you plug in a camera and you say, hey, detect some PPE equipment, for example, like hard hats, well, we have a model that does that, and it'll detect hard hats, and you can then decide whether you want to record that, report that, or send alerts. And what we're doing is developing models where people can start and quickly deploy without having a machine learning expert or a data scientist in the loop. And we can then work with them to do transfer learning so they can add their data to our models and build a very custom model in a very simple way. And so we reduce the complexity of starting AI, developing AI, and deploying AI.
And one of the challenges that a lot of people are facing is that systems are no longer just static. They're all changing. And it's not just the chip that you're working with. Here, it may be the system that this chip is going into. It may be the regulations that are changing and the protocols and all the different elements that will affect how this device behaves within the context of other systems. This addresses it, right?
So this addresses part of it. This addresses the AI aspect of it, and it makes it very scalable and deployable. So as customers have to navigate the environment they're in, or that their products have to be developed or change over time, by having, models that are ready to deploy or that are easily retrained for their applications, it makes that whole development, management, and life cycle of the product easier to do.
So given all of this, basically what you've got is you've got a lot of data and you're always accumulating more data. And you also have to understand how that is going to be impacted as you have changes in protocols, changes in how this system is going to behave in the context of another system, and changes in algorithms in other systems. How does that affect what you're doing here?
So yeah, data is key to the AI model, and customers are always gathering it. Data will change over time based on the use cases, because when you introduce AI, you're now introducing something new into the system, and that all by itself creates change. So that data is going to continuously be updated. And what we're doing is really making it efficient to take your new models, so data, create a new model. We're making it very efficient to be able to test that model, optimize it and quantize it, and then be able to deploy it to the edge. So the systems that we're putting together and our software that we put together makes that deployment really, really easy. And over the life cycle of a product, you may want to update the model on a daily basis or a weekly basis. So that development flow and the ability to be able to capture the data, make the changes and push it back out is critical. And that's what we're doing with our tools. And the chipset, being very, very efficient at the edge from a hardware perspective, allows you to take advantage of that reconfigurability and programmability, so that as a model gets more complex over time, we'll continue to be able to run that, or different models may come out in the future. And we believe we've built a hardware capability that will be able to run any of those models efficiently at the edge.
Barrie Mullins, thanks for a very interesting conversation.
Ed, pleasure talking with you today. I really appreciate your time.